Yes. So I guess I used k because this was part of an inductive thing, but yes. And I guess the original statement is gone, so I don't remember where, I don't think I even had an n or a k in the original statement. All right, just every integer is odd or even. Okay, so we got everybody okay with this? Definitely something you should be able to do for the test, right? Because it's very, very systematic. So again, as you go through this, just think ahead, and before you do your homework, work through this, right? It's really not that bad. And how do you remember what to do, right? How do I remember this? I don't sit down and memorize every detail. What you remember is, okay, you start, and it's a natural thing to do, start with the natural numbers, do that by induction, consider 0, consider negative numbers, and use the first case, okay? So that, what you need to do in this class is reach the stage where you can remember that little short thing, every step of which is pretty natural, right? It's something that you really should automatically think to do. And then know that you can figure out the details, okay? So I mean, that was just, you know, like 10 seconds worth of stuff that I just said. And when you write out the details, it's this, but it's all very systematic, okay? So you're developing your brains to be able to do that. That's the main goal in this class, yes?
I guess one question I would have is, for when you're doing a k, you do for k's in the set of natural numbers, but you're using m and the set z instead of set m.
Because what are we trying to prove? We're trying to prove that it's odd or even. Now I could go on and say, well, yeah, it's going to be a natural number, but that's just extra, right? The whole goal of this is to prove that these numbers are odd or even. And the definition says that that number m is an integer. So if I do that, I'm done, okay? You can go back and observe that, well, yes, it's going to be a natural number, or actually 0 in the base case, right? So there's maybe a reason right there where you want to make sure that you allow integers, right? Because in the base case, it actually was 0. But I'm just checking the definition and observing that in the inductive step that it's in n, that's fine, but it doesn't, right? We're lazy in here, right? And we don't want to, you know, do anything that we're not called upon to do unless it will get us some kind of advantage, okay? So, yes.
So, I guess what I'm saying is z has positive and negative numbers.
Yes.
But n does not.
Yes.
And what confuses me is you have a k. I guess is k ever defined to be in the natural set?
Well, I mean, I think part of the, I mean, maybe this is going back to the other question and getting caught up on what letters we use. Okay, so what we're doing, we're starting with proving it for n by induction. I mean, you can go back and change all those to little n's if you wanted to, but the argument is exactly the same. So what we're doing is we're showing that a natural number is even or odd. And it doesn't matter whether we call it k or n or m or little truck, although that would be weird in terms of, you know, describing the arithmetic, okay? But what we call things is not important as long as we're consistent with what we call, you know, start calling something, we keep calling it that, and we don't give a new thing the same name unless we're done with the name, right? Okay, so yeah, so this part I used k, this part I used n, but we're always just talking, in this case we're just talking about natural numbers k, and over here now, these are all actually negative numbers n. In a way, it might even be more confusing to use k here and k there, I don't know.
Well, what I think was confusing was that, I don't know if like case 1 we have k is even. We have k, and that k, which is a number in the natural set.
Right.
To m, a number in what is it?
So what we're trying to do here is verify that this is even, okay? And the definition says that we just have to write it as k equal 2 times some integer. And so, yes, when k is positive, this integer will happen to be a natural number. But that doesn't matter, right? I mean, that might be useful in some other situation. And in fact, we often use the fact that, you know, if we have something even that we want to, and this is positive, we want to observe that that's going to be positive also. But it's not necessary for this proof, right? All we're trying to do According to definition, all we have to do is show that k is equal to 2 times m for an integer. And we're going to see this come into play big time in the next very big proof, because there, even when we have a natural number, there are going to be negative numbers coming in. Okay? So that's why every time using the definition, it's in z, it's in z, it's in z. And yes, it's in n in some situations, and over here it's negative in some situations, but I want to have one statement that's good for everything. And so that's why I have it in z. Okay? We got one last thing to do, and that's the never both. Okay, so suppose, let's do proof by contradiction. Let's do the never both part, right? So suppose n, an element of z, is both odd and even. Okay, you may not know what to do at this point, and this seems ridiculous because, yeah, you learned in 3rd grade that numbers are never both, okay, but we actually are going to prove this now, and it will use something, not completely trivial that we already did. But even without knowing what you're going to do, you now know what to write down, right? Since it's odd, we can write it how? Okay, some m, an element of z, right? Okay? And since it's even, we can write it how?
2k plus 1.
Yes, k, okay, right. So if we put an m there, it would be really easy, right? But it may not be the same thing here, right? Yeah, I mean, if it were an m, then we'd be, what did I say here? That was odd. Oops, yeah, 2k, yes, okay. But as I said, if it were an m, it'd be really easy because you get 1 equals 0, right? But it's not, it's something different. Well, what would be the next obvious thing to do?
2 plus 1 equals 3.
Yeah, so 2m plus 1 equals 2k. Now, how are we going to get a contradiction? You thought this was easy. Well, we don't like to divide in here.
Multiply both sides by 2 inverse.
Same thing. Remember, dividing is a bad idea, okay? Well, what you're trying to say is that, a half is not an integer.
Oh.
Well, but, I mean, do we even...
By 2m? Because then you have 2k minus 2m equals 2m.
I think this is what you said. Subtract 2m from each side.
Yeah.
And now what?
Pull out the 2.
Pull out the 2.
And then you have,
So by definition, what does this imply?
that implies that k minus m is equal to 1/2.
1 is even.
1 is even. Or, in other words, 2 divides 1, right? We want to stay away from those fractions because even though you could work it out in this case, what we're doing coming up shortly, you're just not going to want... So if you're ever thinking about fractions or dividing, just don't do it. Just say no. Okay? Just say no. Just say no to dividing. Okay, so, right? And what's wrong with that? One of the first things we proved about dividing is what? If something divides something else and they're natural numbers, what does it tell you about those two things?
Is also natural.
If something divides something else and they're natural numbers, what's the relationship between those two
The
numbers?
second one is greater.
Yeah, 2 is less than or equal to 1, and we have proved that, right? Which is a contradiction. So they can't be both. Questions about that? Okay. So I could ask you on the test, show that a natural number cannot be both odd and even. Nice slick little thing. And then I would expect, although I would hope against it, that I would see some halves piling up in there. And like I said, you know, but then you'd have to be, you know, verify some things about that 1/2, and it's, you know, it is possible to do it that way, but not recommended. Okay, so now we're going to talk about the greatest common divisor, and I discussed it a little bit last time. We're going to need, for this argument, we're going to need something here. We're going to need an exercise that you're going to prove at home. It says that if A divides B and A divides C, then A divides AM plus BN for any M and an element of Z.
You mean C
C, excuse me. Yes, sorry. That's B and that's C. That's a mess, yes, right. Okay, yes, thank you. So what is this telling me? Well, so if you've had matrix algebra, you've heard of linear combinations, right? So this is really a linear combination of B and C. There's one huge difference between the linear combination here and the one in linear algebra. And what is that? When you dealt with linear algebra, linear combinations, matrix algebra linear combinations, what were the coefficients? So in this case, the coefficients are M and N. Those of you who've had matrix algebra, what kind of numbers were they? Actually, what were the vectors? The vectors were B and C, right? So B and C were vectors, and you did a linear combination, but what did you allow M and N to be? Those could be real numbers, or if you got that far, complex numbers, right? So those were the coefficients, and they could be an R and C or other fields, okay? So you guys know about fields now, right? You can talk about vector spaces over any field. And the theory is identical, essentially, although weird things happen when you know, well, anyway, I won't get into that. But in this case, though, M and N are actually integers. Okay, so when we're talking about integers, this is still a linear combination of these two, but the coefficients have to be integers. The linear combinations you already know are extremely important in mathematics. If you've had matrix algebra, then you know that, right? And so this is going to say something, this is going to be very important in the next statement, okay? So this is one of your homework exercises. If A divides each of the two numbers here, then it divides any linear combination of those numbers where the coefficients are in Z. Not hard to prove, but that's one of your homework problems, and we'll use that. Okay, so let A and B be an element of Z. Then A and B have a common divisor, D. So that means that D divides A and D divides B with the following properties. Okay, so the first thing you may be thinking, this is greatest common divisor. Okay, GCD. I'm slightly dyslexic this morning, okay. Only had one pot of tea, so maybe that's the reason. With the following properties. Now, of course, you're thinking greatest common denominator, well, that means it should be the biggest. Well, we'll get to that eventually. But the most important property, and this is actually the property that lets us do all the rest, okay. So D is actually a linear combination of the original ones. And again, I think I mentioned last time, when I saw this, I thought, what in the world? First of all, you know, how can you expect to be able to find a common divisor that's in that form? That just seems bizarre, and given that, why would you care about that? Well, it turns out this is actually the essential property. So once we have one of those guys, then we can get one that's non-negative just by, well, if the one we started with was negative, if we negate it, we still got a common divisor, right? Because of the plus or minus lemma, okay? So we can always make it bigger than or equal to 0. And then the third property is if C is a common divisor of A and B. Well, we're going to get to the greatest part in a minute, but if D